So Lennart Augustsson, I guess all of you know him. I think he's the one in this room or any room who has written the most number of Haskell compilers till now. Yeah, but that's not all he's done. I looked at I didn't look at ChatGPT. This is not that conference. I looked at Wikipedia, yeah, and it looks... And it looks, I mean, Lennart Augustsson is a Swedish computer scientist. Okay, everything good till there. But he has worked in many places, including Credit Suisse, Standard Chartered. So I guess you're half Swiss already then with the banks, yeah. Facebook, X-Development. I was wondering what that was, and it is an American semi-secret research and development facility. So you'll have some questions on that from me. Google, and currently at Epic Games. This is great, right? Yeah. But what I didn't know is that he was intimately involved in the early development of the multi-user dungeon. More questions for you? It sounds intriguing. And device drivers. And here are the list of some of your compilers. That's great. And also winning entries in the language C for the International Obfuscated Code Contest. Respect, respect. Yeah, so he's not just famous in our community, yeah, but in many others as well. Thank you very much, Lennart, for agreeing to give the opening talk here. And yeah, I'm looking forward to it.
Thank you. Well, this worked. It's back. So I'm going to talk about MicroHs, a small Haskell compiler. So we can start with the title. Is this a compiler for small Haskell? Or is it a small Haskell compiler? Well, it's a bit of both. So the title is nicely ambiguous. So I'm happy to take questions at any time, but since we have microphones and things, that might not be practical. So I'll try to stop now and then for questions, and people can run around and find a microphone.
Or you could repeat the question if it's short.
Yeah, if I can hear it. So I always start my talks about this the same way. Is this big enough to read? I can make it a little bigger.
I think that's it.
Okay. Yes, MicroHaskell. So I will start by installing it. Well, actually, I will start by downloading it from GitHub. Okay. Oh, I have to change directory. Otherwise, I wish it were that quick, but... So what is it doing? Well, so it comes with some C code, that is the compiler. So it uses the C compiler to compile that. So you get a Haskell compiler. And now the Haskell compiler is recompiling itself, just to be on the safe side. I mean, it feels good to compile itself. And then you need some base libraries. So now it's compiling the base libraries. And so I'll talk more about it, but it uses combinators. So this first thing, it sort of translates your Haskell program into combinators, which I'll describe a bit, and then spits those out in a C file, just as a byte string, and then the C compiler compiles that. And then I'll come back much more to how it works. I'm sorry that it takes 40 seconds to install. I wish it were quicker. So installation, I think, should take under a minute. Otherwise, you should be ashamed. Okay, so now we can run it. So if you don't give it any arguments, it just starts up in interactive mode. And so you can do things. Let's do some thing that I always find a little bit surprising. Complex numbers, of course. What is I? I is 0 colon plus. This is how you write complex numbers in Haskell, if you didn't know. So that is 0 in the real part and 1 in the imaginary part. So that's I. Okay, so now we can do, what happens if you take I and raise it to the power of I? Ooh. You get a real number. Weird. What if you take the log of that? You get something that you almost recognize. So the log of I to the I is minus pi over 2. How can that be? Well, it's obvious if you think about it. I don't know. So this is computing with integer and the super slow implementation of integers that is written in Haskell. If you want fast integers, you can change in the make file, so you link with GMP instead of this super slow. But, I mean, who needs big integers anyway? Okay, so what else can it do? Well, you can, let me first, here is some little program computing some factorials. You can say, okay, let me compile that example, and I want the binary to be called exam, X, I don't have time to type the whole thing. Okay, so now we have a binary. It works. You can, if you don't want to actually compile it to something, you can just run it straight away. Let's do, change the...
What is the size of the object that is produced?
I'm ashamed. I mean, this should be nothing. But we can look at the size of the actual compiler.
Most of that's the interpreter, I guess, not.
Yeah, exactly. So the actual compiler binary is 300K. So the example program has 2/3 of that because it has a lot of stuff. And you also get my version of Cabal and CPP-HS, and you can see that they strangely have the same size, but they are actually different. Before I go on, let's compile the compiler with GHC. Come on, GHC, it's not that hard.
This is 00?
This is 02, I think.
Okay.
Okay, so that's 37 megabytes. So it's a bit more than 100 times bigger than the MicroHs binary. I mean, what's in there? I have no idea. So you can, it's also made so that it should be easy to cross-compile things. So you can tell it, use another configuration for which C compilers to use. And minus O, E. You are absolutely right. So, and if you look at this thing here, it's some terrible JavaScript thing, and then there is some WASM code in a binary blob here at the end. And if you want to run that, it runs as usual. Let me make a little more demo here of, do I have it in the history list? No, I have it in the history list. I don't have to type it. Okay, I'm giving some flags here to tell the compiler where to find all the source code. Okay, so now we can import microhs.main. That is, I'm importing in the source code for the compiler. It's about the same speed as GHC compiling. Okay, so now we've loaded the compiler there. So if I get confused, let me set the variable to 1 here. And then we can run. Okay. Yeah, A is not set here. That's good. We're running in the right one. Yes. Do we have a... yeah, it runs. Let me go out of this. Are we're in the right place? Yes, good. Minus ISRC, no, MHS minus ISRC minus I dist M Cabal. Okay, import micro. No, let me set A equals, A is not set, no good, set it to 2 here. Oop. There, I should have that import in the list here somewhere. There.
Not getting that much slower.
No, the thing is, it's not slower. It always runs at the same speed. And the trick behind that is to make the initial one so slow. Oh, I have to start the new one. Yes, A is not set here. Yeah, okay. I don't know why you would want to do this, but you can do this. Okay, we're back here. A is 2, A is 1, and we're back at the prompt. So the question was how much memory does it use? So right now the default is running with 50 million cells, and how big a cell is depends on if you're on 32 or 64-bit architecture. So a cell is 2 pointers. So these are 16-byte cells, so it's 800 meg. So I'm a bit ashamed of memory use also. So I think as someone mentioned, it's not my first Haskell compilers. I've done a few before, so I guess it's all I can do. So I made another one. Why does the world need another Haskell compiler? I really don't care. I'm 40% retired. I have to have something to do, so I'm doing this for fun. I mean, other people might have other ideas what fun is, but I think this is fun. And then again, maybe the world needs another Haskell compiler. I mean, GHC isn't exactly known for being minimal, as you saw with the binary size. But on the other hand, it's hard to not use GHC because everything assumes that you have all the fantastic things that GHC has implemented. So I did have some goal. I wanted it to recompile itself in under 10 seconds. And I'm afraid I failed initially with that on my laptop. It takes something like 11, but I fixed it. I bought another computer. So I have a Mac Mini now. I can really recommend the Mac Mini. I mean, it's rare to hear anyone say that something is worth the money when you buy Apple products, but the Mac Mini, I think, is actually worth the money. It's an amazing little machine. So it can recompile the compiler in about 8 seconds. Yes, so I'm compiling into combinators, pretty much following exactly how David Turner described it in his 1978 paper. So it's almost 50 years old technology. The implementation is fairly small, so I mean, I think it's pretty hackable if people want to do things. It runs on a bunch of things. I mean, it only really needs a C compiler, and so it runs on all the things where I could actually sort of try it on. So these are the things that GitHub provide virtual machines for. It can also run on microcontrollers, so I've run it on 2 little things, one RISC-V and one ARM-based. The runtime system, a lot of things are optional, so if you don't have standard I/O, you don't have to have that included. If you don't have floating point, you don't have that. You don't need to use GMP and so on. So if you want to run on bare metal, you can tell, I want to compile the runtime system with the really minimal things. And then you can sort of do everything with CFFI. And if you care, I don't know why you would care, you can bootstrap the compiler using hugs. There are some people who really care about this. They want to start with this, whatever it is, this 58-byte binary that they put in their computer that makes it possible to enter hex or something, and then you sort of bootstrap yourself up little by little until you have a C compiler, and then with the C compiler you can compile hugs, and with hugs you can compile MicroHs, and then with MicroHs you can compile GHC. No, you can't. I mean, I've not tried, but I'm 100% sure that you can't. Maybe one day. So micro. These numbers are slightly old, but they're mostly right. So I compare 3 compilers. So MHS, that is micro Haskell compiled with itself. GMHS is micro Haskell compiled with GHC, and GHC is, of course, GHC. So the binary size is 0.3 megabytes for MHS, 37 for when GHC compiles it. And I can't even figure out how big GHC is. Maybe it's 120 megs, because it loads all these modules in as it starts up, so it's big. It's about 12,000 lines of Haskell code and 8,000 lines of C code. GHC is more. If you compile MHS, so when it also have to compile all the libraries you use, then it takes 11 seconds. If the base package is pre-compiled, then it takes about 7.5. And GHC compiles the same thing in 10.9. So this is not quite a fair comparison, because that's GHC compiling with optimization. If you set it to -0.0, I think GHC is like 7 seconds, so it's slightly faster. So what does this mean? Well, if you look at how fast is it to compile MHS with the compiler compiled with GHC, well, with the GHC compiled MicroHs compiler, it recompiles in under a second. And with MHS, it's 11. So that means that MHS is about, say, 12 times slower on this than binaries generated by GHC. But since When you recompile the compiler itself, it takes about the same time. That must mean that MicroHs as a compiler is about 10, 12 times faster than GHC. So don't ask me why. Ask Simon. Poor Simon is not here. The other Simon is here. He was involved once. Ask why GHC is so slow. Or you can ask this guy here. So I think recompiling the compiler in under 10 seconds is a good goal. If you can't get that, I mean, 30. So I started with some Haskell 2010, but I had more goals here. I wanted to be able to compile hackage packages. And if you try to do that, you soon realize that you need more than Haskell 2010. So here are the currently implemented extensions. And they're always on. I give you a language. This is the language you get. If you don't want that, you can go somewhere else. Some of these are extremely easy to implement. You just don't check for certain things that could go wrong. Which is a bit sad. Some of them are a bit tricky. So I'm sad when things slow down the compiler. So this new thing, the new string literals with triple quotes to have a multi-line. They slowed down the compiler by more than 1% because I had to reorganize the lexer. It's terrible. And Unicode, do I have a slide about Unicode? I mean, someone said, oh, I couldn't compile my program because it had a Unicode identifier. And I thought, oh, okay then. So Unicode has 1.1 million code points, and you have to have information about each of them. So about 1 byte per code point. So that's 1.1 megabyte. That's 4 times larger than the compiler. I can't have that table in the compiler. Luckily, that table actually compresses to 2K. So by lots of different compression things. But then you have the terrible tables that translate between upper and lower case and so on.
With all these extensions, how close are you to GHC 2024?
How close am I to GHC 2024? I don't know because I don't know what's in that. So the big things that you might want is type families, which I probably do one day. Template Haskell, which I will never ever do, and I won't take patches that implement it. You can have your own fork if you want to do that. I mean, why would you want to go through that pain? I don't know. I just added concurrent Haskell stuff, which is still buggy. I noticed when I tried some more advanced stuff, but it's coming. Yes, a little rant about hackage. It's full of packages that require GHC. So these statistics are maybe, I don't know, 6 months old or something. At that point, there were about 18,000 packages. And I weeded out the ones that had dependency on Template Haskell and GHC prim. Because
Transitive, presumably.
Transitive, yes. Then there's 1,200 left. So, yeah. Okay, I guess I'll have to stick to those. And then I thought, well, I have to be able to build packages, so I need to use Cabal. So I took a look at source code for Cabal. It's written like, ooh, Haskell has all these features. I have to use all of them. It really uses a lot of stuff that I have not implemented. So I wrote my own microCabal instead. Which is really more like microstack because I get the curated list of packages from Stackage and use that. Yes, but then if you, I mean, I have made a few packages compile, and then sometimes I need to have some little fixes to it that have maybe some CPP that checks. Then you can get comments like this from maintainer of packages. My stance is GHC is the only compiler out there. The ship for multi-compiler ecosystem has long sailed away. And that makes me a bit sad. But I guess this is from a person who maintains many packages on Hackage. So I will, in the future, try to implement the features needed to not have any fixes for his packages. Maybe this person is in the room, I don't know. Okay. Just a few words about how the compiler works. So it's not any different from most compilers. There's a lexer, there's a parser, and then the type check box there should really be like 10 times as big as all the other boxes, because that's where everything happens. And then after type checking, you desugar a bit. And then there's a tiny optimization box, because there's only one single optimization in the whole compiler. And then you spit out combinators. And how does this desugaring work? Well, it takes all of Haskell and turns it into pure lambda calculus, plus primitives. I mean, you need to add integers. So there are primitive types, and there are primitive operations on those. But everything else is done with just lambda calculus. So data types, no need for data types. You can encode those with pure lambda calculus. So I use Scott encoding mostly. I mentioned Scott encoding in a moment. Yes, and generating combinators from the lambda calculus stuff, that's sort of straight from David Turner's old paper. So it's maybe organized a little differently from GHC at least. So as you compile, every module you compile, you stick in a cache, because, I mean, if you compile, say, 10 modules, they will all import the prelude. You don't want to reprocess the prelude every time. So you can you stick that in a cache. And you have a database of packages somewhere, just like GHC. And then when you're done, you write out your file, and I will show you in a moment what it is. It's just a sort of a textual version of the combinators that can be read in again. And that's spit out as a long array of bytes. So it's really like a string, but you can't have string literals that long in C. But you can have long arrays of bytes. And then you take that and you compile that together with the runtime system, and then you have a binary that you can run. Yes, so there's no separate compilation in MicroHs. So, well, not of individual modules. You can compile a package. And what do you do when you compile a package? You compile all the modules that are in the package, and now you have a cache that contains all the stuff for that. And MicroHs can serialize anything to disk without any it's sort of built into the runtime system. So I just take that cache, I serialize it, write it to disk. How do you load a package? You unserialize the cache from disk and just merge it into the cache you have right now. It's very easy. So being able to serialize and deserialize anything is really cool. I mean, you can do it, well, anything is not quite true. If you have pointers into C code, you can't serialize those. I mean, where would they point? You can also tell the compiler that I put all the things that from this compilation. If you're working on a project, you can say, okay, when you've compiled, write the cache to disk. And then next time you start up, it starts by loading up that cache. And then it checks which files have been updated, and it recompiles those. So it means that even if you don't have separate compilation, this sort of gives you the same thing. Compiling the compiler itself, let's say, takes 10 seconds. And if you do it this way and you've made some trivial change, then recompiling it maybe take 3-4 seconds, depends on what you're changing. If you're changing a module that's sort of at the bottom of the hierarchy, of course, then it has to do everything. Yes, data types. How many people know how Scott encoding works? Oh, okay, that's like half maybe. Okay, so let me illustrate by pairs and first and second. Here's how you do pairs. The pair function forms a pair of A and B, and what is that? It is a function that takes a function as argument and applies that function to A and B. So it has A and B squirreled away in there somewhere. And then how do you do first? Well, AB is the pair, so you take AB, which is a function, and you give it the function that will get A and B, and you return A, and second similarly. Nil and cons, similar. Nil, it now takes two arguments, one nil thing and one consy thing, and it returns the nil thing. And cons applies the cons continuation, if you will, to x and x's, and here, that's how you do null and head. And in that way, you can encode any data type, so there's no need for any data nonsense. Here are Booleans. Let me do a little demo just so there is this extra magic command called cprint that gives you, it shows you the combinator graph for an expression. So one, it's printed as one, #1.
Is that a normal function? It doesn't have a colon before it. Is that...
That's a normal function, yes. It's in the IO monad, so it can do whatever weird things you want. So it just serializes the expression you're given, and serialization produces ASCII, so you can show it. What about false? Oh, it's just a K combinator. I've not shown you the combinators yet, but I will in a moment. What about the const function? Oh, it's the K combinator. What about nil? Oh, it's a K combinator. The ID function, it's the I combinator, of course. The flip function is the C combinator, and I only do one more because it's too tedious to do the S combinator. So function composition is the B combinator. So not everything is a single combinator. I mean, that would be ridiculous. So let's say that's something mysterious. That's something else.
Do cprint.
So this is usually what happens when you overflow the C stack. So I need to do something about this so that it ends in something nicer. This is a very frequent output when you try to do something that turns out to be enormous. Yeah, there are flaws. But in principle, it should work. Yeah, if you want to do Scott encoding and get all the types right, you can do that with some new types. And new types don't introduce anything. And you need new types, and you need rank n polymorphism. So this way of doing data types, that's the way it was done in Ponder around 1979, 1980, something like that. So this is not a new idea. It does. I do switch to different encoding when there's a lot of constructors, because otherwise it gets a bit. It's bigger and it's slower. If you use Scott encoding everywhere, it's about 30% slower. Okay. Who knows about a question?
Can you do JDTs with those encoding?
Can I do what?
JDTs.
Oh yeah, absolutely. Can I do GADTs? Yes, GADT was on the long list of extensions. Yes, it has it doesn't care about the underlying substrate. Who knows about SKI combinators? Oh, it's a lot. Okay, that's good. Then I will go through this fairly quickly. So the basic ones are SK and I, and you can see what they do. So I is the identity function. It just returns its argument. K throws away its second argument. And S takes the X and it gives it to both F and G. So here you can see you can use something, you can throw away something, and you can duplicate something. And that's all you need. Actually, you don't need I. You can code I as, for instance, SKK. But it's stupid to do so. It's stupid to only use SK and I. And these were invented in the 1920s by Moses Schoenfinkel. And then a lot of work on combinators was done by Haskell Curry. So I think it's appropriate to use combinators. This is sort of the whole algorithm for turning lambda expressions into combinators. I won't talk about it. Here are some more combinators, all suggested by David Turner. Well, B and C are older than that, but he suggested the S prime, B prime, C prime. And some simplification rules. So if you don't use more than those three combinators, things get ridiculously large. They can get ridiculously large now too. So I think worst case complexity is that it goes n square in the size of the input lambda expression, but that doesn't seem to happen.
This is not the one optimization.
No, sorry. Yeah, there are these optimizations are sort of on the combinator level. So yes, there is one optimization that would be regarded as more a normal compiler optimization. If there's time, I can talk about it, or you can ask me afterwards. Yeah, as you can see, it's important to have these, otherwise it gets ridiculous. There are other ways to do these kind of things. Oleg Kiselyov has some way of doing it. So here is the whole set of combinators that I'm using. So they fit on a page. There's also a lovely book by Raymond Smullyan called To Mock a Mockingbird, where every combinator is a bird, and he talks about how they do different things. And you can learn about combinators without knowing what they are. And there are the names that Smullyan use here. The S is the starling and K is the kestrel. The identity combinator is the idiot bird. It only repeats what it got. Yeah, I will skip graph reduction. I will mention something nice that David Turner already observed, that it has this, what he calls self-optimizing properties. So if you take some function here like 2 plus 3 plus x, and you turn that into combinators, you might get something like this. Int add, and then int add 2 plus 3. Now the first time you run this function, the int add 2 and 3, that will get reduced to 5. And that will remain reduced to 5. You will never do that again because it didn't depend on the argument. So why is this good? Well, if you think about overloaded functions in Haskell, they get past some dictionaries as the first arguments. And given just the dictionaries, you can do all the things at runtime, selecting the right field out of a dictionary, that is the method you need and so on. You can do that without having the other arguments to the function. So those things are independent of the other arguments. And then this property will automatically make sure that you never do those again. So all the sort of dictionary specialization that GHC goes through lengths to do to make programs faster, they happen by magic with combinators. The first time you run the program, all the dictionary stuff, it just goes away, and you never do it again. So they automatically become specialized. So let me make a little function. Increment, it goes from num A, A arrow A, inc x equals x plus 1. cprint inc. And if, say, I want inc with integers, you get this. The inc function itself has dictionaries and stuff, but once I sort of said, oh, I want it for integers, then that goes away. So cprint does an evaluation of its argument. So the dictionaries that were there, they were sort of got incorporated into the code. I can, but it won't be what you think it should be, because as soon as you mention inc, the type checker will go, yeah, I don't see what type this should be. Oh, so I'll default it to integer. And so you will get to see the integer version if I do that. And I'm just afraid that will die. So, yeah, it's too big. I really need to fix that. This is embarrassing. Let me do it for inc, the thing that you expect to see instead, because it can be done, but it's a little, you have to be a little more involved. Import data constraint, inc d. It will now take a dictionary of a num a, an A to an A. Oh yeah, an inc d. It takes a dictionary and then it calls inc. So this just sort of reifies the dictionary into being an actual argument. And now if we cprint that, so that's how increment looked before it was specialized. So if you give this the num dictionary for int, say, then you get that other thing. So I think this is cool because it was a lot of stuff I didn't have to write. It was just there by magic. Yep.
Could we also see inc with a required type argument so it doesn't get specialized? Because you said if you just use inc, it will specialize to integer?
Yeah, but that's the one I showed you here.
Yeah, but if you do for all arrow, because you implemented it, it will get defaulted, right?
Yes, but will that help? Yeah, so he asked if I could do it with a required type argument for all with an arrow. I don't think it will help. We can look at that afterwards. I want to get through some more slides. Yes, I did this demo. Oh, there's exactly the one expressions that you saw on the screen are on this screen as well. Oh, this is out of date now. Oh, but you won't know that, so. It's changed with concurrent Haskell. So there is an evaluator. It sort of evaluates pure terms, and then there used to be one that evaluated IO actions. It's now baked into the other eval. So this is the C code, heavily macroized, that deals with the combinators. So it's not much. I mean, then there are like 80 more things that are all the primitive operations, like all the integer arithmetic, all the floating point arithmetic, byte stringy stuff, malloc and free and blah and blah and blah. But the core is this. So if you run and check how long it takes to do reductions, on my Mac Mini that has an M4, it takes about 3 nanoseconds per combinator reduction, which I think is astonishing. Modern CPUs are fast, yes.
How do you deal with
Seek. I insert seek, and seek is a built-in combinator. It can't be defined in the Lambda calculus, so it's added. It just does eval on the first thing and returns the second. So it's really pseek. Yeah, exec, IO, blah, blah, blah. Okay, memory management. As I said, everything is done with cells. There's no fancy copying garbage collect or anything like that. It's a simple mark scan, except there is no scan. I'll tell you in a moment how it works. So every cell has room for 2 pointers, and I steal a bit to know if it's an actual cell with 2 pointers or if it's something else. So if it's an application node, it points to function and argument. And then if it's some kind of combinator, like S combinator, then the first field contains a numerical thing that says it's MIME the S combinator. If it's an integer, then the second field contains the actual integer. If it's a pointer to C-land, then there's a pointer to C-land. And so how does garbage collection work? You mark all the nodes that you can reach from your pointer stack, or actually you could start just from the root, that would be enough. But you don't mark them in the actual memory that has the cells. There is a separate bitmap that has 1 bit per cell, and that's where you mark that this one's taken. And when you've marked them, you're done. Then, when you want to allocate the new cell, you go to this bitmap and you take the first word and see, is there any unmarked things in this first word? Okay, then that's the cell you'll get. And if it's nothing in the first word, you look in the second word. I mean, of course, you keep track of where you last looked, so you don't start from the beginning every time. And this works very nicely on modern CPUs that has the find first set instruction. You just get the word and you say, find me the first bit that's set. And then you know, okay, it says either it's there or it's not there, and then you have to go to the next word. It's really fast, and garbage collection time is like, I don't know, 10% or something. Let's MHS minus I, MHS minus I, source minus I, dist, Cabal. I'm sorry about the long compilation times. What? Is it the dash? How annoying. Okay. So there are some interesting statistics here. So, and when it started up, the whole combinator graph was 93,000 combinators. So 93,000 combinators is all it takes to encode the Haskell compiler. That's not much. There's not much information contents in a Haskell compiler. It allocated about a gig of cells, had 25 garbage collections, did 2.5 gig of reductions. And you can see at the bottom there, it's 1.55 GC time out of the 10.8. And it did allocated byte strings and things, and created a thread and killed the thread.
Does the GC do reduction? Is that last bit there? Is that
Yes, so the GC can do some reductions. Yes. So there are some reductions that you don't want to have in the main reduction loop because they're kind of slow and they're not super beneficial. But when you're doing garbage collection, you're slowing down anyway, so you can do a little more fancy things. You can turn those off. It makes not much difference.
Does that also give you like this? Oh, you don't have. Yeah, there are no fields. Never mind. Okay, yeah. Select optimization in GHC, but I guess you don't have.
I don't know what you're talking about, so it's fine. As I said, you can serialize everything, and it's really easy. It's because you have this graph in memory. There are only 2 kinds of nodes, well, 3. Application nodes, some primitive operations, and some base type things. And so it serializes that and keeps sharing and cycles by doing a 2-pass algorithm to see where you have shared nodes. And as I said, it can serialize everything except pointers into C-land. I have found serialization to be super useful. And I mean, you can serialize something and you can then load it in on a completely different kind of machine if you want to. The serialization format is sort of machine independent. The serialization primitive is, it's nice, takes a handle, takes anything, spits it out. The deserialization, it's super type unsafe because it takes a handle and says, I can give you whatever you like. And if what you like is not what was in that file, well, that's your own fault. You can probably hack up something that does something more type safe than this. You could at least serialize something of type dynamic, say, that includes the type.
So you have typeable then?
I have typeable, yes. But that's not really enough because you need to know that none of the data types you've serialized have changed between when you wrote it and when you read it. So you really need some kind of fingerprint of every single data type in your program to be serialized together with it. And it works for what I'm using it for. If someone wants to make some safe thing on top of that, I would be thrilled. I'll take those patches as long as they don't use Template Haskell. Yes, as I said, the runtime system is quite portable and easy to move to new systems. Yes. So the micro can also be thought of as being microcontrollers. So I have one here. It's a small ARM, I think.
How much SRAM?
I think it has maybe 256K, maybe 128. So it's signaling MicroHs in Morse, and it's changing the color a little bit. And it's written in Haskell, of course. So this is my pathetic demo. Olivier Lischer, one of Farad's students, he has done something else with a microcontroller. And he's here somewhere. Yeah, so go and talk to him if you want to see something more impressive. I've never seen it. I want to see it. I have contributors. I don't know who all of these people are really. But it's fun to get patches. I would especially like to thank Consumlam. Is he here? Or she? I don't know. Okay. So this person sends me For a while, there was one patch a day, sort of things that I'd forgotten to implement or did it wrong or whatever. And another person I'd like to thank is Jan Mason, because he sends something now and then, and every time he sends something, things speed up with like 5% or so, and that's amazing. Yes, you can download it and play with it. If you want to hack on something on it, you can talk to me. Here are some possible things of different varying degrees of difficulty. All right, that's all I have, but there might be questions.
So historically, people were quite interested in building hardware to directly execute these kinds of expressions, right? Do you think we went wrong somewhere, right? Going down the risk path instead, and should we turn back and build some hardware to execute these things directly?
So, I'd like to echo Arvind, who sadly died last year, saying, it's really about the loads and stores. And yeah, you can build hardware that improves some things, but it's really hard to improve the loads and stores. They are going to be there, and functional programming uses a memory a lot. So yes, you can probably make it a little bit faster. I don't think you can make it enormously much faster. There is someone took MicroHs and switched out the back end for something else. I can't remember the names now. They're in Scotland, and made some FPGA and ran. So yeah, did we go wrong? Yeah, I mean, it would have been fun to try another path, but I'm not sure it's now. I think it's hopeless because modern processors are so fast. They put so much work into them. It's hard to catch up with all that. It would require some really big company saying, okay, we're going to go all in on Haskell, and we're going to make these 3 nanometer chips that execute them directly. But I mean, that's not going to happen. So, okay.
So I was wondering about the JS runtime system. Do you have one, or how does it work that you can run the web page?
It just takes the C code that you would normally give to the regular C compiler,
I see.
and you give that to EMCC, and it spits out something. I don't know how it works. I didn't even write that part. Someone contributed that and said, here, now you can run it with JavaScript and WASM. And I said, okay, thank you. And it was sort of no changes to the compiler. It's just sort of a makefile change, basically.
Have you considered some way of annotating native pointers so that you could define a serialization and representation for them?
So there is a table with one entry at the moment in the serialization code that handles some special pointers that it knows what to do with. But yeah, so you could do that.
So in your heap representation, how do you manage variable length things like byte arrays and mutable byte arrays and all that kind of, given that you've got mostly fixed size
They are
cells?
done in C, and I allocate them with malloc. And they are a pointer, so it knows about that byte strings are allocated by malloc and that they are byte strings. So they can be serialized. You just spit out the bytes.
And then they get freed when that cell gets freed?
Yeah.
Right, okay.
Yeah, I mean, it's done with foreign pointers with the finalizer. The same with if you use GMP and have big nums. Yeah.
Yeah. Hello. So I have a question. I've seen a presentation by Cornel Elliott about compiling to categories, not combinators, categories, with a similar goal of producing C code. Is that related or competing, or can you place it roughly in the landscape?
I guess it's related. I mean, there are some categorical combinators. You could compile to those. That's how Camel started, they were compiling to categorical combinators. Is it competing? I don't know. I mean, I like these. I'm happy if other people want to try different backends with different kinds of combinators. That would be great.
So first I'd say, you said you were embarrassed for several points, and having been the one who probably contributed to quite a bit, and my colleagues, to that 300 megabytes or whatever that GHC takes on your hard drive now, I think your embarrassment doesn't even match the, But I think really your design is great in that it is very consistent. The combinator-based design makes serialization very easy and gives you a nice clean compilation and interpretation story. But I guess you are clearly 3 nanoseconds per reduction. Still, it's quick, surprisingly quick, but still not that quick compared to actually compiling 2 object code. And I wonder, maybe I recognize it's a much different design, but how would you start to move in a direction where you could begin to see a bit move towards an object code or potentially a different design that doesn't give up many, maybe all the benefits of a combinator-based design, but still gets better with time?
There is a possible project. I didn't put it here because I think it's very difficult. I'd like to have a JIT.
Yeah.
Something that says, oh, this combinator blob here, we've used that many times. Let's see if we can generate machine code for that instead. So I think that could probably buy you a factor of 2 or 3. The thing that you can't do is to do something good with data types, because you lost all knowledge about what the constructors of the data types are and so on. So I mean, you only have these combinators. They could have come from anywhere. So as you saw, K is the representation for nil and for false and whatever else it was. I mean, so it's things you'd like to do you can't do anymore. So this is my project for fun, so I do this when I think it's fun. Sure. I might do a JIT.
Yeah, so I have a few questions about performance. Like here.
I don't even see where you are. Oh, there, okay.
Yeah. Like one is, like profile-guided optimization in MicroHs would be something like running the program once with stubbed out I/O, trying to cover every function, and then cache that and package that, right?
Yeah.
Is that what you're doing, or are you like at every startup doing the optimization?
At every startup, it does the optimization.
So there's like low-hanging fruit still for you to get better by trying to stub out I/O and run once before cache.
Yeah, so something I wanted to try, I haven't tried it actually, is that the compiler before exiting, it can say, okay, now I want to serialize main. And stick that in something, and then see if that runs a bit faster next time. But I don't think it's much of a difference, because I mean, the optimizations you do once, they're pretty quick. But I don't know. I'm frequently wrong in predicting
like
performance.
Maybe recompiling GHC in MicroHs, maybe that would profit from this.
Yes.
And then another one is like, did you try reshuffling your C-eval case statements, like trying to get the hits first and then like that might be another performance.
Yes, so I haven't tried that. I think Jan Willem Mason has tried that, because one of the patches he sent me was basically an observation that it did some unnecessary switch at one point that you could avoid. So I looked at the machine code or the assembly code, and I'm not sure reshuffling them would change things, because it looks like it's using a jump table.
Okay, and the last one, really. Like, did you try to get your combinator output compressed and kind of guess the entropy from it to see if you need more or less combinators?
So I did some sort of manual inspection, well, manual with a little program, inspection to see if there were some frequent patterns of combinators that maybe deserved their own combinator. So that's how I made a few of these that are non-standard, like Z and some others. And I tried, and it's a fine balance. Sometimes when you add an extra one, it actually goes slower rather than faster. And when it comes, by the way, to size, the thing that is written to to file. I mean, you can write the sort of the ASCII, but I actually have a little Lempel-Zev compressor that compresses this so that it gets a bit smaller, the thing that's stored in the byte array, rather than this sort of shrinks to a third or something like that. Okay.
So you mentioned S expressions. Have you considered looking at using, I don't know, Common Lisp or Racket as a intermediate step?
I haven't. That could be an interesting exercise. Not generating combinators, but just generating Racket or share scheme or something like that. I guess that's what they use, I think.
Okay. A final question.
I didn't understand how I/O is represented in combinators. Could you say a bit more about that?
So I can tell you, yeah, the story is almost the same. So there are combinators for bind and return, and then they are interpreted by the runtime.
So just combinators that you treat specially that can do I/O?
Yeah.
Thanks.
Good. Thank you very much, Lennart. Let's thank the speaker again. Okay, just give us about 20 seconds to set up for the welcome presentation, and yeah, we'll continue with that. Thanks.